Hello and welcome to the AddMorePower Project. Today we have met up with a project partner from KU Leuven. Hi, please introduce yourself.
Yeah, so my name is Martin Diehl. I work as an assistant professor at KU Leuven in Belgium, in Leuven. And I actually work at two departments. So we are here at the Department for Computer Science, where I'm affiliated with 50%. And the other 50% is just around the corner at the Department for Materials Engineering. And yeah, combining those two things makes clear that I'm most likely work in computational material science, which is actually true. And there I work at the continuum scale. So I'm not really concerned with individual atoms, but with scales of micrometers up to millimeters that are relevant for many engineering applications. My traditional, my background is in the field of metals research for structural applications. So I worked a lot on dual-phase steels together with Tata Steel and during my PhD. And now I'm entering the fascinating world of semiconductors with AddMorePower and coordinating the modeling and simulation work package.
Thank you. Can you tell us a bit more about KU Leuven?
Yeah, so KU Leuven is located in one of the oldest university cities, university towns in the world. So we have a long history of having education at university level in Leuven. There's no continuous one university, so we cannot claim to be the oldest university in Europe. But if you go to the city center, you certainly see that many old university buildings are there. There's, for example, also the Groot-Begainhof, which is now the university housing, which is also from medieval times as the university. And yeah, but we are also a modern university, so campus here is newer, where all the engineering and science is located. There are also humanities, mainly in the city center, and biomedical sciences here at the KU Leuven University Hospital.
Interesting. Back to AddMorePower, what's your role in this project?
Yeah, so as the overarching responsibility in Work Package 5, I also coordinate the modeling and simulation. That does not only include the team here, but also researchers at KAI, to some extent at Infineon, IPM from Czech Republic, and LEM3 in Metz. So I try to I try to bring them together and make clear that we all work in the same direction. But locally here, I'm supervising Javier, who is a PhD student, and we do the multi-physics modeling. That means because the problem is complex, so we have temperature, we have diffusion of impurities, we have mechanics, plastic deformation, elastic deformation driven by the heat that is asserted to the metallization plate. And all things work together. In the end, we have void formation, where we currently develop the model to describe that. And all things need to be developed, implemented, and then put together. And this is my research interest, to really develop models that are predictive and can help to understand the lifetime, predict the lifetime of the device.
Awesome. What's the progress so far?
So we started to implement the model, and one aspect of that is that we want to deal with the complex geometries that we find in the devices. And most of the testing is not done directly on the device, but on this tool called polyheater. But these complex devices, complex geometries that are represented, that represent the actual situation in the device that is sold. And to make this possible, we need to use finite element modeling. And we made a lot of progress on importing complex geometries. We also established a good connection with another research team that is developing the tools that we use as the base for our model. So this is called PETSI. And with the PETSI people, we had a lot of improvements on the geometry and meshing. So all the auxiliary tools that we really need to do the work that we finally want to do. Besides that, that is an achievement that was done within Work Package 5, mainly by the KAI team and the IPM team. And they really did experimental work in this simulation work package to figure out what is actually the mechanism that leads to the void formation. And we could clearly show that one of the hypotheses that we had, namely that it's driven by gas pressure, is very unlikely to be the case. So that is really something that helps us to develop the model.
Fascinating. So what do you think is cool about this project?
For me, it's really the first time that I work with power semiconductors or semiconductors in general. So I find it really fascinating how also in this area you can do super interesting metal research. What is special about AddMorePower is really the combination of high-end characterization techniques, high-end modeling, bringing all these expertise together to work on one specific problem.
Absolutely. What are you most excited about?
Yeah, I think this year we will make huge progress again, and then we really can see how the things come together. So we will implement the new model into the simulation tool that we use, which is Damask, where I'm working on for my whole career. So there will be new releases with new features that are then also open to the scientific community. So for example, what I mentioned before, this FEM solver is now getting into a state where we actively want to advertise it, to get feedback from external users that help us to understand better how stable it is, how useful it is, what is not so good at the moment, and we can improve it. So there, having these releases of Damask is always something that is very exciting for me, because then we have, getting new feedback, getting new users is always important.
Nice. Anything else you want to talk about?
Yeah, I'm really looking forward to the next 3 years to work together with all of you, with the whole AddMorePower team, and getting exciting experimental insights that help to build better software.
Thank you. And for our audience, if you want to know more about this project, head over to addmorepower.eu.